Welcome once again, everyone, to the webinar today. If you don't know me, my name is Megan Guidry. I am training lead for NeSI, and our webinar topic today is Who Needs GPUs? Tips for determining if your code is a fit. We will have NeSI research software engineer Alexander Pletzer presenting the webinar today, and he will introduce himself properly in just a moment. But before that, let me quickly go over some basic housekeeping. So while Alex is presenting, we just ask that you make sure your audio is on mute so that there isn't any background noise. But if at any point in time you have a question, please pop it into that Google document that I posted in the chat. I will post it once more so that you have it up on your screen. Did that work? There we go. Ooh, I might have posted it too many times now. So that's where we're going to be posting our questions. But of course, if Alex pauses and says, hey, unmute yourself if you have a question, we might have moments like that too. We do have some helpers on standby as well, ready to answer your questions and type responses in the document. Lastly, the webinar is being recorded today, and the recording will be posted to NeSI's YouTube channel. The link to the YouTube channel is at the top of that question document in the resources tab if you're curious about other webinars that we've done. But if you don't want to accidentally appear in the recording, just make sure that your video stays off. I think that is mostly it from me. So Alex, if you'd like to take it away and kick off the webinar.
Yeah, thanks, Megan, for kicking that off. So my name is Alex Pletzer. I'm working for NeSI at NeSI, and I've been involved with sort of porting some codes to GPUs, and I'd like to share my experience. Of course, I'm not the only one who has that experience. So, you know, some of the questions that you may ask might have to be answered by somebody else, but I'm very happy to share essentially whatever I know. Let me just, since we're talking about sharing, maybe I should share my slides. And let's go to the slideshow here. Can everybody see that? Yeah, all good. Yeah, so this is, you know, things are sort of changing a little bit in the computing arena. There are things called GPUs, graphical processing units, and I think what I'd like to explore with you is whether this is a technology that would be useful to you as a researcher. The involved in that sort of effort, there are different people. I mean, one is Chris Scott, with whom I'm working very closely on a particular project. Maxime Rio is a data scientist who has used has provided some of the slides, as well as Wolfgang Hayek, who's working at NeSI. We also work with researchers. One of them is called Damien Mather from University of Otago. He's in the marketing department, and Gilles Bellon, who's at University of Auckland, and we're working with him on a sort of a reduced quasi-equilibrium climate model. Georgina Ray and of course the NeSI team were all instrumental in you know, in getting the GPUs running at NeSI, so we're very much indebted to them as well. So just to get the ball rolling here, something has changed, and something has changed around 2004, 2005, and not everybody may be aware of that, but you know, older people like me, I mean, they remember the good old times. The good old times was when you didn't have to work very hard to get your code run faster, and faster. Really, all you had to do is sit on your hands and just wait and buy some new kit. And at that point, the code would actually run faster. That's really no longer the case. I apologize, this picture is a little bit, it's the original picture of a paper that appeared in 2005, if I'm not mistaken, yeah, by Herb Suter in Dr. Dobbs' journal. And The curve that I really want you to focus on is the blue one, and it's a logarithmic plot, right? Vertically, and then horizontally, the x-axis we have the years, so it's pretty old, so it stops at around 2010. But I think the whole the picture hasn't really changed that much, so it's very much a valid picture. Vertically, you have some numbers, and for the blue curve, those numbers represent the clock frequency. So 1000 represents 1 gigahertz, sorry. So what you can see is that, you know, from the 1970s all the way to the early years 2000, I mean, there was a nice little progression of the clock frequency, and that's how computers got faster. The clock frequency is basically what sort of times, essentially, you know, every instruction is performed, you know, within a clock period. And so if you have higher frequency, you're going to perform more instructions per second. But then it stopped, and it stopped because things were heating up, and that's the other light blue curve which is underneath. And so we reached, you know, about 100 watts for the processors, the CPU. And it was sort of impractical to go beyond. I mean, you know, you start to cram more and more transistors in a much smaller, very small volume, and I think it heats up, and having 100 watts, you know, in a very small volume starts to be a little bit the limit. So we had to address that, right? People had to address that. And Herb Suter, when he wrote his article, which was called "The End of the Free Lunch is Over," you know, he decided that it was very clear from his point of view that something had to be done, that in order to run faster, because everybody wants to run faster, then we had to do something else. And the something else has been basically 3 things that we can do. So we can do vector operations. So, you know, a lot of calculations involve vectors and matrices, and you can take a vector, which is just a collection of numbers, and you put that in a pipeline, and then you apply operations to each element of that vector simultaneously, and so you can get some speed up, but it is fairly modest, and maybe a speed up of 2 to a factor 5, maybe 8. I haven't really seen that. Potentially could be 8, but typically it's a factor 2, 3, 4, 4-ish, maybe at most. Then the next thing that you can do is, well, the clock frequency hasn't really increased, but we have more processors. So let's just harness all these processors via shared memory. So all these processors, they access the same memory. All your data is in memory, and they all can work in parallel. But of course, they have to access memory. There's a little bit of contention here. But nevertheless, you know, you can get a speed up of maybe, you know, 10, 20, 50 is a bit of a maximum here. Because that's the number of cores that we have per node, which has now, you know, increased. Is going to increase maybe to 64 on the 28 maybe in the future. So, you know, pretty substantial speed up. And then the last thing that you can do is using MPI, which is the message passing interface. That's just one technology, but there are other ways of achieving that. And that's called distributed computing. Now you have really different computers, not only just CPUs sharing the same memory, essentially within the same box, but now really physically having different computers, and they all talk to each other and they synchronize, and that is highly scalable. There's essentially no limit. It's the hardware limit. It gets harder and harder to scale, but there is no theoretical limit to that. So that's all great. But then there's something else that came into play, which are called the GPUs, or the graphical processing units. And everybody has heard about Moore's law, which means that computing power increased by, you know, doubles every 2 years or 1.5 years or something like that. Well, this is a purely empirical law, right? I mean, there's no theoretical sort of grounding in it, but it's something that has been observed over decades. Well, the graphical processing units, they're actually evolving, they're actually improving faster than Moore's law. So there's something called the Huang's law, which is like 25 times faster in 5 years. And from Moore's law, we would have expected a factor 10. So, what are these GPUs? We've been thinking a little bit about good analogies, and there are several of them that are pretty good. So this is one of them. You might have seen other ones, but if you are somebody who grew up, I grew up in Europe and in the 1970s, and they used to read these comic books, Asterix and Obelix, and these are sort of like two little characters. One is sort of the bright little guy, that's Asterix on the left, and Obelix is a bit of a sort of a dim-witted, but he's very, very strong. And Asterix, I think, here represents the CPU. It's something that is very polyvalent, can do a lot of different things, really smart things. But when you really need brawn, when you need power, then the GPU can actually come to your help. And so GPUs take instructions from the CPU. This is why Obelix is sort of a bit dim-witted. He can't do really things on his own. He sort of has to take some instructions from Asterix. So a CPU does not need a GPU, but a GPU needs a CPU, in other words. A CPU is very versatile. You can do anything. You can run a word processor, you can run games, you can do scientific, very serious scientific computation. You can do lots of different things. But a GPU is sort of a little bit more specialized. It's ideal for simple operations, meaning that the vector operations, vector matrix operations. That doesn't mean that with simple operation you can't do something that is complex. So I want to sort of emphasize that aspect. If you can do something simply, but very well and very, very, very fast, then at that point you can do something more complex, very complex, in fact. And so the other thing with the GPUs is that they're really great for scaling up. The fact that a GPU is specialized means that it's not going to run, your word processor. It's not going to be a great thing to do. It's going to be really good at specific tasks. That's what we say. But these tasks actually could be quite important in science as well. So different ways that GPUs can be leveraged. So we have GPUs. We're going to talk about that in the next section. But we have GPUs at NeSI, and in your head now, I think you want to start thinking about, how can I use them? So we think that there are about 5 ways you can use a GPU, and as we're going down, it gets harder and harder, but maybe the benefits are higher and higher. So the first thing, or not necessarily, in fact, the first thing is that you're given a code that is already compiled to run on the GPU, so just use it. And you might have a code from chemistry. You might be doing machine learning like PyTorch or TensorFlow. But I think there's an increasing number of these tools that actually support GPU architectures underneath. Number 2, maybe you code links to a library that is GPU enabled. So, you're writing some code and now you're doing an FFT, a Fourier transform, or you're doing some operations, you're calling PETSI, some of these libraries, Pioneers. And maybe they have a GPU version, which runs, has been optimized. So you can just link against it and everything should probably just work. Or with very little effort. So it's sort of more a question of changing the build system of your code. Number 3, you decide that you're very happy about the CPU, but there's some parts of your code that just run like a dog and it's slow and so forth, and you identify those as being ideal for running on a GPU. So if you identify the for loop, that could benefit, then you could use OpenACC or OpenMP 4.5 to offload the computation from the CPU to the GPU. Right? So again, remember that the CPU is that orchestrator, that's Asterix, Asterix decides everything. And then occasionally Asterix, has more work than he can handle. So he's going to hand over the work to Obelix, who's got these really powerful arms, and that's the GPU. Fourthly, and this is sort of like emerging technology. I don't personally have a lot of experience with that, but I'd like to hear if people have used that. But there are things like Cocos or SYCL for C++, and they essentially allow you to write C++, but with some sort of abstraction layer, which allows you to offload computation to a GPU as well. Finally, you can re-implement some of the kernels, some of your calculations in CUDA or OpenCL, which is sort of like a hybrid language C. There's a Fortran version as well for CUDA. That's getting harder, that's more work. So I don't know exactly where you sit in terms of your research, but I think that's an important question to ask. So before I talk about GPUs at NeSI, we can have a little break here and see if there's some questions that come up. If people can just read the questions for me, that'd be great.
Thanks, Alex. No questions in the question document at the moment, but we can see if any kind of action starts with this prompt. If anyone has questions about the slides Alex has covered so far, you can also unmute yourself now if you want to ask verbally.
Yeah. I mean, we can always, of course, come back to any of the slides at the end. So.
Hi, Sean here.
Sean, hello, Sean.
Hi. So since you mentioned CPUs are a lot like GPUs, so I was wondering if there's any way we can monitor the performance of the GPU. Like for CPU, we can monitor how many cores are being used and what kind of memories are being used. So for GPUs, is there some measures we can use to monitor the performance of the GPU and how occupied it is?
So it could be there are different answers, I think, to your question. One of them. You might be talking about Slurm profiling. I'd have to check whether Slurm could be made aware of that. But definitely in terms of profiling tools, MAP I think will give you that. But NSIght, another profiling tool for NVIDIA, will give you that. And I think that's a really good question. Sort of a little bit more advanced. That is, once you developed your code and you want to figure out, how much memory, what's the performance, and also, how much data traffic you're getting between CPU and GPU. I think profiling tools are pretty good at that.
Yeah. Yes. Yeah. Thank you for your answer. I saw someone is typing on the question doc, saying that we can use NVIDIA SIM on the supercomputer to monitor the performance of GPU. However, for NeSI, we can only open up an interactive sessions on the GPU node, right? Because what we are running the code is actually we are running on the gateway computer rather than actual node, is it?
Yeah.
Yes. So when we type NVIDIA SIM, it's actually on the gateway rather than on the actual node.
Yeah. You could connect to the node and just type your command there. Perhaps if you know exactly. I mean, you get that information when you submit the job. But you're right. We're going to talk a little bit about GPUs at NeSI. Maybe that some of it would clarify. But I think I don't have a specific slide for you, Sean. But it's definitely something that we need to maybe there's a need for another seminar that would go into these details. Yeah. Maybe let me So go through a couple more slides here and see if they answer at least partially some of your questions. The two GPUs. I mean, the first thing for people to realize is that we have two sets of GPUs installed at NeSI. We have the P100, they have been installed. They have been part of our platform since we did that upgrade 4 years ago. And they're really good for code development. They're really good if you're having an older code, an older version of TensorFlow, for instance, that does not run on the latest hardware. So that's a good choice. And typically everybody will have access to these GPUs. On the right-hand side, we have the NVIDIA Ampere Tesla 100A100 that have been installed recently. They sort of top of the line, and we have found them to be maybe up to 3-4 times faster than the P100 for the best applications. But some applications run about the same speed on A100 compared to P100, and we can talk about why that's the case. But it's definitely a better GPU. It's got more memory. So one of the drawback of the P100 is that the memory is a little bit limited, and so not everybody could use the P100 that has more memory, 40 gigabytes versus 12 gigabytes. And once you have more memory, you have more choices in terms of what software to run, what workloads, and so ideal for production work. But you'd have to apply to get access to the A100. So at NeSI, if you what do you have to do in order to you have your code, you have built your code, you want to run it. What would you have to do to run on the GPU? Well, you have to add that directive GPUs per node and equal something colon something. That first something is either P100 or A100 for the newest, and the column here, the number after the column is the number of GPUs that you want to use, because for some applications, you might even be able to use several GPUs. So again, maybe if somebody has a question, so we can, is there something that pops up, Megan?
There is some continued, I think, discussion around the question we had before. I'm not sure, Chris, I can see is typing. I'm not sure if he wanted to jump in and add anything or.
Oh yeah, sure. I could just say quickly that you can actually connect to any node that you have a job running on in Slurm. You don't need to start an interactive session there. Just from a login node, you could run SSH node name, and then you'll be able to get connected to it. Yeah, that's all I was typing in.
Thanks.
Yeah, that's very helpful. Thanks.
Cool. But if there are any other questions, if anyone starts typing anything, we can pause and wait for that to come through. Otherwise, doesn't look like anything's coming in. So why don't you go ahead, Alex, and we'll cover questions at the end.
So now I just want to go through sort of our limited experience at this point. Like every new technology, the A100, but also the P100, it's still a learning process. It's a learning process for everybody, for us, for the research and so forth. And I wanted to just share with you, some sort of pieces of software that have used CUDA, have used GPUs, and to what extent they have been successful or not. And so I would say that if you're doing machine learning and you're using something like PyTorch or TensorFlow, then I think you should be able to benefit quite a bit. So we had a case, and that was provided by Maxime Rio, our new data scientist at NeSI. He looked at a model that had over 300 million parameters. And here the benefits of the A100 over the P100 were, were important because he had more memories and then he could use a larger batch sizes or tackle larger problems. So the result of that is captured in that particular slides. On the left-hand side, you have that vertical bar, which is the dark blue one. That's the reference, the wall clock time, so hours. So there was a training that took close to 16 hours on the one P100 batch size of 4. And just moving to the A100, the newer version of the GPU, meant that this was it was a factor 2.5 faster, and but now you have other avenues, to further improve the performance. And I'm not going to go through all the little changes that were made, but for some reason the slides change without me pressing anything. Apologies. But on the right-hand side, you have the little pink sort of a little vertical bar, and I think it's less than an hour. So here Maxime was able to go from 16 hours to 45 minutes, and he was using 2 A100, and he was using a much bigger batch size from 4 to 32 because he had more memory, delayed updates, and so that's a factor 20. Use case number 2, that's a tropical circulation model, which I mentioned at the beginning. The bottleneck was identified as being a large dense matrix times dense matrix times dense matrix multiplication. And we, first the code was using matmul, that's a Fortran intrinsic function, moved over to BLAS, then from BLAS to CLU-BLAS, which is the CUDA BLAS that runs on the GPU. When we did that on the P100, we had a performance that became comparable to 16 CPU cores, but we didn't see much improvement when we moved to the A100. We had to do a little bit of profiling, and that may be answering Sean's question. We used the map profile. I don't have the data right now, but from the map profile, we identified that there was a significant cost of migrating the data from the CPU to the GPU and back. And so the GPU was running great, but there was all that transfer of data that meant that a faster GPU just wouldn't pay off. And we're currently looking into porting some larger parts of the code to the GPU. That's work in progress as part of a NeSI consultancy. Use case number 3, this is Chris worked on that, and it's a really interesting code. I mean, first because the area of interest, marketing, I think we had never worked in that particular area, so it was new to us. And we had a researcher who, for things that I don't fully understand, but he had to compute a very, very large determinant of the determinant of a very, very large matrix. And he had started to do some implementation in Fortran. So that's when Chris came in, and he, apologies, and he, added MPI and OpenACC directives to it. So the code was actually running using MPI and GPUs at the same time. Got some really nice speed up of 13x, and found that one A100 GPU was performing similarly to 160 physical cores. Okay. So, and also there was a benefit in using the A100 for that particular problem, was running 3 times faster than the P100. Use case number 4, that's a a benchmark code that we've been developing over the years. It's pretty quick, but it represents basically the computational pattern that many codes go or have, you know, finite element codes, finite volume, finite differences. They all seem to have, you know, a communication pattern that involves a computation on a particular cell and then getting some information from neighboring cells. It's advection, and it's a pretty lightweight code. We originally, I think, when we ported it, we were very happy. We had an improvement of 20x, but we were able to do much better than that. If we ended up with over the serial version, a speed up of 600. And I have to say that when the code ran, I wasn't quite sure whether I was pretty convinced that something must have gone wrong, because I don't think I've ever experienced a 600x speed up over serial. But ran it 20 times and was able to see that, yeah, the results were produced and they seemed correct. So I had to do some visualization and all kinds of checks and checksums and things like that, and everything looked fine. So the plot on the right hand side, so the blue, so this is speed up. It's not the whole clock time as before speed up, so the higher the better. The blue, that's the baseline. Then when we move to the P100, that's the orange one. We got you know, a factor 100 something, and then when we, again, logarithmic scale, beware. And then when we move to the A100, the green bars, we got 600, and so it's 3.5x compared to between the A100 and P100. You know, pretty nice and so forth, but already you get a lot of speed up from just migrating to the GPU. Now, the thing that was interesting here was that all you had to do was add a couple of what are called fragmas, and that's sort of shown on the left-hand side in magenta. So fragma ACC data copy. Essentially, you have to tell the compiler that you want to migrate the data onto the GPU, and then just, you know, do all the calculations on the GPU, and that's how we got the this great speed up. The you know, OpenACC, that was what I showed before, was OpenACC, but actually now we also have OpenMP. One of the latest version of OpenMP allows you to overload offload data. And we were given, it's a different GPU. It's the AMD MI100. We had a chance to play with. It's a different compiler as well, but it's exactly the same code. And you know, we got a pretty decent speed up as well, 30x. The pragmas are a little bit more complicated. We're not 100% sure whether we did, you know, the best, we produced the most optimal code. So bear in mind that this is still work in progress. In principle, OpenMP 4.5 and OpenACC are very similar in terms of functionality. And so we expected to actually get about the same performance, but give or take, you know, a factor 2 or so. But that's not exactly what we observed. Nevertheless, I mean, you recognize, you know, some of the pragmas like Pragma OMP parallel 4, very similar to the one on the on the previous slide. You know, Pragma ACC parallel loop, very similar. All right, this is it, and after that I'll just have a summary. But again, I like to just stop in case some questions come up before we have the summary.
Cool, thanks, Alex. And there is another question that has popped up, but I see that Maxime is in the midst of typing a response. I might have scared him away though because it stopped. Okay, there we go. So Maxime, did you want, I don't know if he's actually in this Zoom room, but if he is, he could potentially share what he's typing. Let's see. I don't see him in. So we'll wait for him to respond. In the meantime, if you have a question, please type it in the document. Before Alex goes on to his summary, I did also want to ask people in the room, if you wanted to put in the chat, like what brought you to this webinar? Why were you interested to learn more about GPUs? We would be really fascinated to hear what brought you here, because we're working on providing really great support for people interested in GPUs, maybe using GPUs for the first time. So if you wanted to share what brought you here today, it might help us get a better understanding of who's kind of on the fence, maybe interested in using some of our resources, and we can maybe even chat about some of these situations. So would love to hear from you. Right, so no other questions for the moment, Alex, if you want to continue on with summary.
Sure. Yes, and you know, as Megan said, I mean, I think we like to work with your researchers, and so you know, the particular topics of GPU computing that you'd be interested in, then that could become material for another webinar in the future. So the take-home message is that GPUs can bring potentially huge rewards, sometimes, you know, modest, maybe, well, quite decent, you know, factor 10, 20 or something like that. So that's all really good. And that potentially can improve your research. One of the, you know, the learning curve to use GPUs in the past was pretty high, because people had to use CUDA programming. They had to learn like a new programming model, and it was fine-grained and required quite a bit of skill. Well, I think one of the message that we want to send you is you don't need to know CUDA in order to be able to leverage GPUs at NeSI. The next, I think, is if you're thinking about whether your code is suitable for GPU or not, I think you have to start thinking in terms of structured computational patterns. You know, something that is very regular. We're talking about matrix vector operations, you know, regular loops and so forth. Something that would not be very regular would be maybe graphs and, you know, with lots of edges and things like that. You know, if you have a node, you don't know exactly how many edges each node has. And so that's going to be probably more challenging to port on a GPU, although there are some libraries that are being developed, and so just stay tuned. So even if something looks like it's going to be difficult to port to the GPU, that may not be the case in the future. Beware of the computational cost of migrating data from CPU to GPU, right? So typically what you want to send all your data as much as you can possibly on the GPU, hold on to the data as long as you can, and just minimize the transfers. I mean, it's a bit like having two houses, and you it's easy to just you know, sleep a couple of nights in one house and go to another house and sleep in the other house. But if every time you move to your secondary home, you have to carry all your furniture with you, then I think it's going to be quite impractical. And I think that's also the case for the GPU. We talked about OpenACC. That's just one technology. But the nice thing is that you can combine it with MPI, or you can even combine it with OpenMP threads. So you can play, you know, at different levels at the same time. Just because you're using OpenACC doesn't mean that you can't use MPI. We have that great example from marketing, which shows how this is possible. And OpenMP threads, you know, they work okay. You can do that. We have had some experience with OpenMP 4.5. It's sort of early on for us, and we don't regard ourselves as being expert in that area. So it's quite possible that we did something wrong and that somebody would say, whoa, you know, it's much better to do it, you know, in a different way using task or, you know, whatever. And so we happy, of course, you know, to hear feedback from your researchers as well. So the big question, let's go back to that original question that we had, should I run on a GPU or CPU? Well, I mean, some of it will always have to be on the CPU, but by that, I mean entirely on the CPU or CPU plus GPU. Well, the A100, first of all, so, you know, apart from, okay, so there are different things, is you know, there's a certain cost that is associated with running on the GPU. So we have compute units, and at this point, you know, the P100 is about 20 times more costly than a single physical CPU, physical core. So you want to get, you know, a speed up of 20x or more to make it worth. Now, the A100 would potentially give you even more than that. And the A100, they cost about 2.5 times more. So that's sort of the determining factor. But keep in mind that the A100 at this point, they're not accessible to every allocation by default. So you have to talk to us and try to convince us that whatever you're running could benefit from the A100. I think in the near future we will open them, the A100 after the next upgrade. But currently it's a limited resource. So choose your hardware to minimize your compute unit usage. That's essentially the bottom line here. Of course, we never know ahead of time, and it's also possible that today your code might run 20 times faster on the GPU, but you might still want to run on the CPU. But tomorrow might be a different story. And the GPU, as you remember, the GPU they seem to be evolving faster. According to Huang's law. So rolling out we talked a little bit about the A100, and also we mentioned that some new A100s are coming up. The new ones will have 80 gigabytes, and they are going to be installed as part of the Mahuik extension. You know, there's a little case study that's a little link at the bottom here that you may want to take a look at. And if you're interested in the technicality of installing these GPUs, all the issues about heating and power consumptions and so on and so forth. But finally, I would say that yeah, I would like to hear about your GPU experience. Of course, if you've been using GPUs and you know, what's your take. And finally, that we have a consultancy program that potentially can help you. And so if you have any questions, whether it's about GPUs or other things, you can always send an email to support@nesi.org.nz, including if you want to apply for try to get access to the A100, and in general, for any question, we always very happy to hear about your experience. Thank you.
Thanks, Alex. That was great. Really good information. And I'm having a look at the question document. There's a really nice chat about a specific question that I'm leaving to Maxime, because it seems like he has all the details. But let's have a look. A couple of people have commented their GPU experience so far. I won't call anyone out to share verbally unless they feel like they want to. But initially, there was someone in genomics keen to better understand background to the technology, how to set up parameters appropriately. and so far has had a good experience with getting support from NeSI. So that's really nice to see. And please jump in if anyone also wants to share or ask a question.
So in terms of parameters, let's if we go back to that I think settings, LUM setting, that's the only thing I've used so far. I mean, on top of the GPUs per node, I would sometimes use QoS equals to I can write it here, QoS, maybe something like that. S batch QoS is equal to dash, okay. Debug, potentially. But I never, essentially you just have the whole memory. So you don't have to specify any maximum memory. It's a little simpler than for the CPU, where we encourage users to declare how much memory they need, because that's going to determine whether they're going to find a slot in the queue. Not sure if that partially answers the question in terms of settings. There's, of course, in the code, there are sometimes settings that people use to determine the number of gangs and vector size and so forth. So I think that's probably left to a more advanced seminar or webinar. Cool.
Thanks, Alex. Yeah, and I think that might have been kind of a comment more than anything. So yeah, really good information. And one other comment in the chat. So this particular attendee has experience with toy DL modeling for a while and has used a few public playgrounds like Colab. I hope NeSI is a better fit for me to learn the full potentials of DL modeling. Just getting started with the help from Albert. So yeah, good shout out to Albert. Thanks, Albert. NeSI support. Woohoo.
I have to ask Albert what DL stands for.
Yeah, it's a mystery to me too. I'm not sure.
Deep learning.
Deep learning.
Deep learning. That's, of course.
Thank you, Albert.
Silly.
Very bad with acronyms.
I know. Okay. No other questions for the moment. I'm going to do a little bit of a wrap up. So a couple slides. And if you have anything that pops up in the next 2 minutes or so, you still have a chance to ask a question. So just pop it in that question document. But I will go ahead and get my slides shared so that we can wrap up and get you guys on your way. All right, so there's my housekeeping slides again. We did questions, getting support. So that is the main bit of our webinar today. Before you would go, though, I'd like to point out that there are a bunch of resources in that question document and in the chat. I'll see if someone on the call, maybe Jana, if she's still on the call, can put some of those links in the question document so that they don't disappear once the Zoom session ends, and that you can get to some of those. The Tech Insights blog posts and some of those other nice, meaty resources. And just remember, another call out, if you ever need support, have a question, emailing support@nesi.org.nz is the best way to get in touch with us. We will connect you with the right person. So if you email us there, you'll be able to get your questions answered. Of course, check the NeSI website for the recording of this webinar. I'll post it in the next day or two, and also send you an email once it's posted if you registered for the webinar. One last call out. So if you enjoyed today's webinar, there's a good chance you would also enjoy the New Zealand Research Software Engineering Conference, which is happening from the 15th to 17th of September, all online. Submissions for the conference are open until this Friday. So if you're keen to be involved, maybe even submitting a presentation, please do so by Friday, or you can just register to attend and learn lots of good bits from the community. It's a really fun one, and we're looking forward to hosting that one in September. The link to the conference website is in that Google Doc as well. And thank you so much, Alex, for presenting at the webinar. I'm having a look at that question document, and there aren't any other questions for the moment. So that's it for the webinar. Thanks everyone for attending, and hopefully we'll see you at another webinar soon. Have a great afternoon.
Hey, thanks, Megan. Cheers.